Let's start with the problem, like we often do, because life is full of problems. But thank goodness we have math to help answer our questions. Determine the value, or possibly values, of A so that the following piecewise function will be continuous. Now we saw examples of this where it says, oh, find A. But what's going on here? We have this function f of x where it's e to the 2x plus 10 sine squared x if I'm below A, and 7 e to the x minus 10 cosine squared x if I'm above A, or equal to A. Now here it's sort of a different type of problem, because previously it's like, oh, you got to fine-tune the function to fit. Now what are we doing? Well, we're going to fine-tune the cutoff. So how do we figure that out? Well, one thing is to sort of say, well, what's going on here? And so we might say, I don't know how to graph this e to the 2x plus 10 sine squared x. Well, let's just think abstractly. I say, well, look, there's two pieces. I'll call this part here, let's say that's g of x, and maybe it does something like that. I don't know. It probably has some sort of up and down type thing, since there's a sine function in there. Then there's this other part, this second part, and I'll call this h of x, and it's doing something. Again, I'm not entirely sure. But that's the intuition. I have these two functions, and the question is, where do I put the cutoff? Well, if I put a cutoff over, say, here, that would be bad, because from the left, I'm on this green part. From the right, I'm on this sort of orangey, reddish part. Is that continuous? No, the green is up too high compared to the orangey, reddish part. Over here, that's also a bad choice. Again, the green part is not matching up. So what do we need to do? We need to find that sweet spot where they cross. This is the value for A, which would make us happy. Because at that spot where they intersect, we'd see that from the left and from the right, things would agree. And that means that we can patch them together without having to lift up our drawing utensil, pen or pencil that we're doing. All right, so now we have an idea. So the question is, where do these two line up? Now, it looks a little bit daunting, but nevertheless, we forge up ahead. E to the x plus 10 sine squared x is equal to 7 e to the x minus 10 cosine squared of x. All right. Well, generally speaking, unless something really nice is about to happen, this is where we'd have to stop. But this is calculus. We expect nice things to happen to us. So we say, all right, let's push everything over. So we're going to move everything. Let's move it to the left-hand side. So I'm going to move the 7e to the x across, minus 10 cosine squared x across. If I do, we'll be able to say that 0 is equal to e to the 2x, and then the minus 7e to the x, and then there's 10 sine squared of x, and then there's 10 cosine squared of x, because when it comes over, it'll come over as a plus. Well, is there anything we can do to simplify?
I think you can put a 10 up front, and then in parentheses you go like sine squared x plus cosine x.
Yeah. So this last piece here, we see it's really a sine squared plus cosine squared. That's one of our favorite trig identities. Definitely it's within our top 6. And you might say, that's an unusual number to pick. I say top 6 because there's only 6 trig identities you need to know to get through calculus. So this is one of them. Now everyone's wondering, what are the other 5? Well, just keep coming. We'll get to them. All right. So now we say, aha, the trigonometry, it was just misdirection to make us think the problem was hard. Mwahaha. So now we just have to figure out, when is this true? E to the 2x minus 7e to the x plus 10. When does that equal 0? Now, this might still look a little bit daunting, but there is an observation to make. And that's that we've chosen to write e to the 2x because we were told it was e to the 2x. But there's another way to write e to the 2x. It turns out this is also e to the x squared. And the reason I point this out is if we think about sort of our fundamental thing as being e to the x, temporarily, we can imagine in our mind. So in our mind, we say, oh, we think about this as something like something squared, let's say z minus 7 times that something plus 10. We say, oh, wait, that's like we have a quadratic. All right. Well, if we have a quadratic, what do we hope should be true? That are factors. Well, does z squared minus 7z plus 10, whoops, does that factor? Yeah. What does it factor as? Yeah, so it'd be e to the x minus 2, e to the x minus 5. So now, because this equals 0, we can conclude, aha, it must be that e to the x has to equal 2, or e to the x has to equal 5. Now, 2 and 5 are not our answers, but we're close. Because what we need is we need to find x. Right now we have e to the x. What do we do to liberate that x from the exponent? Natural log. Yes. So, x equals natural log of 2, or x equals natural log of 5. This turns out it will actually have it crossed twice, so there are 2 values which we could have picked for a. And that's the answer. All right. Well, what's today's topic? Well, today we're going to talk a little bit about limits again. Well, we're getting near the end because it's harder to get much bigger than today's topic. We're going to talk about infinity. Now, oftentimes when we hear the phrase infinity, we might think of something like a little toy saying going to infinity and beyond. Well, no, there's no beyond. We just go towards infinity. Now, a lot of people say, oh, infinity is just a really big number, like 17, But no, infinity is not a number. And that's sort of the thing. It's sort of a strange thing. It really is just, when we talk about the word infinity, it's more of a concept, but what it means is it's unbounded. There's something bigger than that, so that we can keep going. So even the word infinity, if you look at it, the in means not, and then finite. So infinity just means not finite. Okay. So we can now ask the question, what happens as we go towards infinity? In other words, what happens as x gets bigger and bigger and bigger? So that's a limit type question. Now, there's 2 ways that infinity can show up. One way it can show up is it can say, well, let's suppose we look at a limit where the output is infinity or where the input is infinity. So here's some examples. Limit as x goes to infinity of 1 over x. So the x is getting larger and larger. So if I think about 1 over a really large number, what's happening to that? It gets smaller and smaller. And so in the limit, in other words, if we were to keep going this process, I'm getting it closer and closer to 0. And so our notion of limits says that as x gets larger, 1 over x gets smaller, which means it's going towards 0. Another one we should talk about is e to the x. So e to the x, what happens to e to the x as x goes now towards minus infinity? Notice we're differentiate here. There's 2 types of infinity. So you can go to infinity 2 different ways. You can go in one direction, you're going towards positive infinity, which means you're getting larger and larger positive. The other direction, you're going towards negative infinity, which means you're getting larger and larger, but it's negative. So these are different types of infinity, so we have to treat them separately. So here we're going towards negative infinity now. What happens to e to the x? So we're getting e to a really large negative number. What's going on? Think about e to a negative exponent. If I have a negative exponent, what do we do? Put it into the bottom. So it's like, e to the negative 2 would be 1 over e squared. So now, if you want, you can think of it as 1 over e to a really big positive number. What happens to that? So the bottom part gets bigger and bigger. The whole expression gets smaller, which means that this is 0. Don't worry, we will have answers which are not 0 going forward. Maybe. We'll see. So this is visible if you graph e to the x. The function e to the x from 0 on, it has this huge blow up. But then below 0, you're actually going towards the axis. So one of the things to remember about e to the x will always be positive. But as you go towards minus infinity, it's going to trail down. It's going to get smaller and smaller. Go towards 0. Okay, so that's an example where the input was an infinity. Now we can talk about the output. What happens to what happens to 1 over x as x goes to 0, and notice from plus. So x is a very small positive number. What's true about 1 over x? So 1 over a very small positive number becomes a very large positive number. Make my input x a smaller positive number, what happens to that 1 over x? It becomes bigger and much bigger. In fact, it can get as big as we want, which is to say it can grow unboundedly. So what's the limit as x goes to 0 from above of 1 over x? It's infinity. But what happens if we change it? Now x goes to 0, but from below of 1 over x. What happens? Well, the same philosophy in terms of the size holds. What's the difference? It's now negative. So if I have 1 over a small negative number, I'm still negative. So this is negative infinity. And this you can see in the function. So 1 over x, if you graph it, has this shape here. So from above, the right-hand side, it's going up. From below, left-hand side, it's going down. If we combine these two facts together, what can we say about the limit as x goes to 0 of 1 over x? What's true of that? Doesn't exist. Because remember, the rule says that if I want the limit to exist, I have to have both sides agreeing. And positive infinity and negative infinity are as far apart as you can get. Nothing can be further apart. Okay. So the next thing we want to talk about are what are called horizontal asymptotes. Now, a horizontal asymptote means that you're approaching something, and it's, this is what it means. The function is approaching a particular value as x approaches infinity or as x approaches negative infinity. So in other words, the limit, as it says here, x approaches infinity of f of x is some value. That looks like a k. And as x approaches a negative infinity, it's some value. These don't have to be the same. You have to be careful. Whatever your behavior is at infinity doesn't have to be the same behavior at negative infinity. So that means that you get to check. As an example, look at our inputs. 1 over x has a horizontal asymptote of 0 as you head towards plus infinity. That's what this first statement says. If you look at e to the x, it has a horizontal asymptote as you head towards negative infinity. What about positive infinity? Is there a horizontal asymptote? No, because it's not approaching a value. It just grows arbitrarily large. So when you're looking for horizontal asymptotes, the real question is what happens to your function as you head towards infinity? Make sure you check both sides, because you have to make sure they might have different behavior. Now here's the fun part. It might be the case that your expression heads towards infinity over infinity or infinity minus infinity. Now, previously we talked about 0 over 0. 0 over 0 means that we're not sure what it was ambiguous. Now, what happens if you see infinity over infinity? Well, more work. It's the same thing. It's ambiguous. It doesn't have a set meaning. So how do we figure it out? Now, here's how I like to think of it. If we think about one of our basic ideas when we had 0 over 0, we said, okay, let's try to somehow cancel the zeros if we can. We want to do more or less the same idea. We say, look, if I have infinity over infinity, that means my top is getting big, my bottom is getting big, so let's just slow it down. Pump the brakes. You're kind of young. You'd have to talk to your parents about what it means to pump the brakes. But they're old cars. You'd have to work with the cars to help slow them down. If you just slammed the brakes on, it wouldn't work. But you got to just right. So we're going to try to slow the growth down so that we don't have to deal with infinities. Now, infinity minus infinity, well, that's even more work. And oftentimes the way we deal with that is to try to make things into a nice ratio. So let's do some problems with horizontal asymptotes. All right. Find the following. Limit as x goes towards negative infinity of 7e to the x plus 3 over 1 plus e to the x. Well, the first thing to do is just say, what's happening now? We don't start doing any manipulations unless we have to. And we don't know whether or not we have to unless we say, well, what's going on with it as it currently is? Now, the current pieces involve e to the x. What do we know happens to e to the x as we go towards negative infinity? Yeah, e to the x approaches 0. That was one of the things we said. So notice, as I go towards negative infinity, the e to the x is going towards 0. E to the x here, also going towards 0. So I say, oh, there's no problems here. Everything is nice and contained. In particular, we see that if we say, all right, the top, there's sort of a justification that we skip, but we know it in our head, which is to say, okay, I can break it up into the limit of the top, limit of the bottom. I can keep further breaking up. But the point here is that everything is nice. And if it's nice, we can say, all right, the answer would be 7 times 0 plus 3 over 1 plus 0, a final answer of 3. So positive 3, that's our horizontal asymptote as we go towards negative infinity. Okay. Now we're going to ask the question, what about positive infinity? Can we just write down 3? No, we can't. You have to check. You have to do the work. Now, could it be that the answer is 3? It could be, but we don't know, so we have to do the work. Well, let's see what's happening. E to the x as x goes towards infinity. Well, we saw that a few minutes ago. It was getting huge. So the bottom's getting big, the top's getting big. This is going towards infinity over infinity. All right, a classic, more work. So here's how we deal with this, or at least here's how I like to deal with it, and I would encourage you to sort of adopt a similar philosophy. What's driving the growth? In other words, what's making it big? What part is it? The e to the x, right? I mean, if you look at the denominator, there's just 2 terms. You say, well, between e to the x, which is getting huge, and the 1, which stays close to 1, it's the e to the x part that's really making it huge. So I say, okay, so the e to the x is what's causing it to be big. So I need to slow it down by just enough to cancel out that e to the x. So how much do I slow it down by? Well, the answer is, sorry, I'm going to take a second to rewrite this. Ooh, adding drama. What is he going to write down? What could it be? The answer is 1 over e to the x. And we're going to do it to both top and bottom. So it's the classic, I'm multiplying by 1. But multiplying by 1 doesn't change the expression. It just gives it in a different form. So it's still the same thing we're doing. But we're not multiplying by just any 1. We're multiplying by a 1 that's going to slow it down just enough to give us what we need. All right, so we distribute this 1 over e to the x. So this would become the limit. X goes towards infinity. Upstairs, what do we get? 7 and 3 over e to the x. Downstairs, what do we get? 1 over e to the x and 1. Now, e to the x still gets huge, but we look at where it's at in our expressions. So 1 over e to the x, what happens to that as we go towards infinity? It goes to 0. How about 3 over e to the x? Yeah, it goes to 3 times 0. Also 0. 0 is a very powerful influence. Okay, which means that this is now a limit we can handle. So we get that the answer is 7 plus 0 over 0 plus 1, which is 7. So they actually do have different values for the two asymptotes. So that's why we have to check both. Well, that wasn't so bad. Let's try another. All right. Find the limit as x goes to infinity of the expression square root of x squared plus 4x plus 7 minus x. Now looking at this, it's not so clear what's going on here. Certainly if we look at the x, this part here by itself, we see that that's getting huge. On the other hand, the square root of x squared plus 4x plus 7, the inside is getting huge. And we're taking the square root of a huge number, which is still huge. So this is going to a really big number, and we're subtracting a really big number. Now the question is, okay, what happens? Well, the problem is infinity minus infinity is again this ambiguous thing. Why is that? Well, the question is, are they about the same size? Maybe they're just really close to each other so that when you subtract them, they cancel out and be finite. Or maybe one infinity is like really big compared to the other one. And so it gets huge. So it's not clear. All right. So that means, well, no surprise, we're going to have some fun. We're going to do some work. So now our thought is, all right, we can't really, do our pumping the brakes action that we did on the previous problem because we don't have a fraction. And so what we'd like to do is we'd like to get a fraction. And there's something else we'd like to do, which is get rid of that square root. Because square roots are a challenge for us. And they will be for quite some time through calculus. So is there something that helps us both get rid of square roots and turn this into a fraction? The conjugate. Yeah. 2 birds, 1 stone. Square root of x squared plus 4x plus 7 plus x, so I'm going to multiply that on the top, and square root of x squared plus 4x plus 7 plus x, I'm going to multiply that on the bottom. So this becomes the limit as x goes towards infinity. Upstairs, we're going to get x squared plus 4x plus 7. The square roots are going to go away because we're squaring that expression. And then we're going to get subtract x squared. So a squared minus b squared. Downstairs, well, we have that expression, square root of x squared plus 4x plus 7 plus x. What can we do? Yeah, we can definitely cancel the x squareds. And now we're like, hey, we canceled something. Let's check in and see how we're doing. So we check in and we say, okay, now, before we were going to like infinity minus infinity. Upstairs, after our cancellation, what's going to happen? Well, 4x plus 7 goes to what? Infinity. And downstairs, we're going to get a big number plus x, which is going big. So that's going to be infinity. So, well, still more work. And you might think, this feels like we haven't made progress. But we have. You see, because the infinity minus infinity, there's not much for us to do. But infinity over infinity, we have this idea. Pump the brakes. Slow it down. Let's look at the numerator. There's two terms. There's the 4x and there's the 7. Which one is causing it to be big? The 4x. Yeah, and even the 4 doesn't really matter. It's that x. That x is driving the growth. If we could just slow that down just the right amount, then we'd be fine. So what do we multiply by? 1 over x. So, multiply top and bottom by 1 over x. Okay. So that's x goes to infinity. 4x plus 7. Going to multiply that by 1 over x. And downstairs, square root of x squared plus 4x plus 7 plus x. And I'm going to multiply that by 1 over x. And, well, I hope we solve this problem soon. I'm running out of space. Okay. Multiplying by 1 over x upstairs, well, that's not so bad. That's 4 plus 7 over x. Downstairs, the end is not so bad. That's going to be a plus 1. Now we come into the challenge. Okay, so I have this 1 over x, and I have this square root. And what I'd like to do is to somehow push the 1 over x into the square root. So, I would like to say that, so again, let's just do a little bit of side work over here. Square root of x squared plus 4x plus 7 times 1 over x. I would like to say that, boy, wouldn't it be great if it were true that 1 over x is 1 over square root of x squared? So in other words, that I could put it into a square root. I'd like to say that. Is it true? And if it's true, why is it true? So, someone has said they cancel out. That's really good intuition. And that is part of it, but there's one other fact that we need to make it be true. It's positive. So here's that fun caveat that, you can always annoy your younger siblings with. What is the square root of x squared? It turns out it's the absolute value of x. So you have to be a little bit careful. Now, when x is positive, the square root of x squared is in fact x, and we're good to go. But how do we know x is positive? We're approaching positive infinity. So we're trying to get a very big positive thing. So yes, we can assume x is positive. So we're good to go, that we're safe. Now, if x had been going towards negative infinity, what would we have had to do here? We could still do the same thing if we did what? We put a negative sign. Now you might say, they would never do that to us. Well, back in the old days, before I took over calculus, they did it to you. They put it on an exam. But, you're smart. You wouldn't be fooled by that. All right. So, good. So this becomes really a single square root. X squared plus 4x plus 7 over x squared. Or I can write it here. X squared over x squared, 1. 4x over x squared, 4 over x. And 7 over x squared. 7 over x squared. All right, whoops, I'm off the bottom there, I think. All right. So, we are now ready to tackle the final evaluation of this limit. What happens upstairs? 7 over x does what? Approaches 0, so we're left with 4. This is great, because 4 is that sweet spot, because it's not 0, and it's not infinity. So when you have a number, you're like, game over. This is it. Whatever happens, happens right now. All right. Downstairs. The 4 over x and the 7 over x squared, what happens to those parts? They go to 0, so we're left with square root of 1 plus 1. We can simplify this whole expression to 2. And there's the answer. Now, that's half the problem. That is the positive infinity. What about negative infinity? Well, what happens to the square root of x squared plus 4x plus 7 minus x? Let's think about it. What's happening to the first term? It's a really big number. What's the sign? It's going to be positive because it's like we square stuff. You take the square, it's end up being a big positive thing. Then we're going to subtract off. Well, what's happening to x? It's heading towards negative infinity. So we're subtracting off a really big negative thing. Well, what does that mean? If you have a big thing and you subtract off a really big negative thing, it's like you have 2 big things being added together. So what's the result? Infinity. So this is a case where on one side it goes to a nice value of 2. So as we head towards positive infinity, and as we head towards negative infinity, it just gets bigger and bigger. All right. Let's do one more. Find the limit as x goes towards infinity of x times sine of 1 over x. Now, what does this do? You might be thinking, boy, we've hit just about every single combination of x and 1 over x and sine, and well, we're getting close. Only a few left. Let's just think about intuitively what's happening to our parts, because there's 2 parts. What's happening to that x part? It's getting huge. It's like going towards infinity. What's happening to this other part? Well, let's just work our way through our onion here. 1 over x, what's happening to that? It's going to 0. When the inside goes to 0, what does sine do? It also goes to 0, because it's a continuous function. Continuous functions, no surprises. So this is heading towards something that looks like a huge number times a really teeny number, infinity times 0. And when we see infinity times 0, what does that mean? More work. Is there someone going, what do you mean? You should be like, yeah, this is great. I thought I wouldn't get a chance to work in this class. Okay. So the problem here is, the question is, how fast is something going towards infinity versus how quickly is it going towards 0? Depending upon the rates of how these things go to each other, they can just cancel each other out, or one could win in the end. That's why it's ambiguous. And we're going to have to deal with these problems. So we say, okay, well, let's think of it in maybe a slightly different way. Because we know this sine function, in the back of our head, we have this basic fact. Sine of something, which I'll call blah, it's a technical math term, over blah goes to 1 if blah is going towards 0. Okay, so it doesn't matter what the inside thing is. It can be a complicated looking expression. As long as that complicated expression goes towards 0 and the bottom, what's underneath it, matches, then we're great. So the question is, can we use this fact? This is sort of our go-to fact about trigonometric functions and limits. So let's think about our current limit. So limit as x goes towards infinity. Well, we have a sine of 1 over x. What can we do with the x? We can put it down. What would it be? If I put it downstairs, what would it be? 1 over x. Now, what do we have? Well, we have this 1 over x matches 1 over x. Is the 1 over x going to 0? Yeah. So I have my form, sine of blah over blah. Blah is going to 0. So what does this go to? 1. This seems somewhat unsatisfying, and I understand that. So let's do a little thing here. We'll do a change of names. So let's just change our names. 1 over x is going to become a new name. Let's call it y. Well, working our way through the alphabet. This is just to help simplify our expression. This would become sine of y over y, because sine of 1 over x over 1 over x. Now, what happens to our limit? Well, as x goes towards infinity, what happens to 1 over x? Goes to 0. Can we be even more precise? Not that we have to be, but I just want to ask the question. Can we be even more precise? Someone says going positive, right? See, this is the nice thing about infinity. You can only approach infinity from one direction. If I'm going to positive infinity, I can only approach it from below. If I'm going to negative infinity, I can only approach it from above. So in fact, this is a one-sided limit. Now, it doesn't make a difference in this case, but if it did, we're ready to answer the call. And we say, okay, this is a limit, sine y over y. This is something that we recognize. So now in this form, it's easier to convince ourselves that yes, the answer is 1. All right, we talked about horizontal asymptotes, but there are other kinds. So the other kind of asymptote we need to be aware of and ready to talk about are the vertical. So when we talk about the horizontal, that says what happens to the function as you go off to infinity. Now, one small note, I forgot to say this, but it's not too late. If I have a horizontal asymptote, so let's say this is my horizontal asymptote, is the function allowed to cross a horizontal asymptote? The answer is, yeah, of course. You can cross it, you just have to get closer to it. Now, you might say, is there an example of a function that does this? Yes. Here's an example of a function. Sine of x over x is a function. What happens to that function as x goes towards infinity? What happens to the downstairs? Let's just think about it. Downstairs is big. What happens to the upstairs as x goes towards infinity? It stays small, namely between -1 and +1. So if you have something that's small, between -1 and +1, divided by something that's huge, the result will be a very small thing, something that's getting close to 0. But because of the sign is changing value, it keeps going up and down, up and down. So it's okay for horizontal asymptotes to be crossed. Vertical, no. But horizontal, yes. Oh, I mean, can you cross a vertical asymptote? No. All right, so what is a vertical asymptote? Well, vertical asymptote is when our output blows up. So we saw that when we had that function 1 over x, where we said, okay, it's getting very, very large. Now, it's possible you can get very, very large, positive on one side, negative on one side. You might have it where it's very large, positive from both sides. You might have some weird function which is defined piecewise. Maybe it goes down and asymptote on one side, but from the other side, it's just a normal function. There's all sorts of things that could happen. But when we talk about a horizontal asymptote, that really means that the limit is blowing up to either plus or minus infinity. Most of the time, they're one-sided limits because when you have an asymptote, it's very common to have different behaviors on different sides. So we like to look and say, okay, what's happening below? What's happening above? And let's see, is there anything else we need to say? Well, what's the approach? Oftentimes, when do we see this? Well, we see this when we have something that's something divided by 0. And when we see a something over 0, that's not a 0 over 0. Remember, 0 over 0 means more work. But if you have a number that's not 0 over 0, you don't have to do more work. That means that it's blowing up, because you're having a number over something very tiny that causes a blow up. What you have to do is figure out how are you blowing up. And the way you figure that out is you say, okay, it's near 0, but what kind of 0 is it? And I know that's a weird way to phrase the question because you're like, isn't there only one kind of 0? When I say what kind of 0 is it, I'm asking the question, yes, at the limit you're 0, but near the limit, are you a very small positive 0 or are you a very small negative 0? In other words, which side of 0 are you coming in on? Because that will help you figure out whether you're positive or negative. Okay. So, let's try an example, or two. Find the limit as x goes to 1 of 3x squared minus 7x plus 5 over x cubed minus 2x squared plus x. So let's plug in 1. Upstairs, what do we see? Well, we see 3 minus 7 plus 5. And if we add all those up, we see, aha, that's 1. Downstairs, we see 1 minus 2 plus 1. Well, 1 minus 2 plus 1 is 0. So it's 1 over 0. All right. So you're probably thinking, aha, we're done. Well, we now know that something is blowing up. What we have to figure out is how is it blowing up. It is still possible this limit doesn't exist if the two sides have different behavior. They might both have the same behavior, and if they do, we have to figure out what behavior that is. So let's think a little bit more. So let's figure out what's happening downstairs. More closely examining what's this piece. Is there another way to write that expression? In particular, can we factor it in a nice way? Okay, so certainly the x can come out and it becomes x squared minus 2x plus 1. Can we go even further down the rabbit hole? Yes? Okay, how? X times x minus 1 squared. Okay? So now let's think about what's happening here. So what I want to do to figure out the behavior is I want to really say, okay, if I'm near 1, is this 0 coming from a very small positive or a very small negative? Okay, so let's think about, I'm a number near 1. Will this x be a positive or negative? It's positive because I'm near 1. What about this quantity x minus 1 squared? It's going to be a positive number because, yes, I subtract 1, so I could be on either side, but then the square helps say, be optimistic, be positive. So what happens here is that this part right here, this is always greater than 0 for x near 1. And on the upstairs, what do we have? Well, because it's going to 1, we know that this part is near 1. Because whatever the upstairs goes to, that's where it's going to be close to. So I have a number that's near 1 divided by a number that's positive, but near 0. So what's the result going to be? It's going to be a big number, but is it a big positive number or a big negative number? It's a big positive number. And that's regardless of which side I fall on. And therefore, the answer is that this is a limit that exists, and it's going to be infinity. All right. Find the limit as t goes towards 0 of 1 over t sine of 1 over t. Okay. Well, this should be fun. All right. Well, we remember the part sine 1 over t because we've seen this a couple of times. This is that function that comes off from infinity and then starts to oscillate faster and faster and faster as we move in towards 0. So that's just sine of 1 over t. Then there's this other part right here of 1 over t. Now, one of the things we can do is we can think about this as sort of a squeeze, is that I have this sine 1 over t that's going up and down. And so I can say, well, where is it going up and down from? The answer is that the sine 1 over t is going to go up and down to this curve. Well, more particularly, it's going to go either up to positive 1 over t, or it's going to go down to negative 1 over t. I'm just going to draw it from the right-hand side. The left-hand side is very similar. So when you have this sine 1 over t, it's saying, look, I'm going between positive 1 and negative 1, which means that the expression is going between positive 1 over t and negative 1 over t. And here, this might help if I write it this way. So because sine of 1 over t is between 1 and negative 1, then 1 over t sine 1 over t is between positive 1 over t and negative 1 over t. Just multiply everything by 1 over t. So the moral here is that what happens is with this sine 1 over t is it really oscillates between two curves. Now we used that in squeeze theorem once with this problem. I think it was a quiz problem where we got two curves that was oscillating in between, but those two curves were coming together and we're like, oh, this is nice. We're going to squeeze it and life is good. But now we're going to say, no, it's going to oscillate, but not between two curves that come together. It's going to oscillate between two curves that are going apart. So what happens? Well, what happens is it starts to do this. And I'm going to use a lot of ink. So this is sort of the most extreme case. What happens to the limit as t goes to 0 of this expression? It doesn't exist. Now, the reason we say it doesn't exist is it's not going towards one specific number. It's going towards a range of numbers. What's the range of values it's getting close to? Yeah, everything. As t gets close to 0, it gets close to every possible value. So this is like, you know, likes to make friends with everybody. I'll be your friend. Yes, I'll be your friend. We'll all be friends. All right. Find all asymptotes for the following function. X squared plus 4x plus 3 divided by x squared minus 2 absolute value of x plus 1. Now for this function, you might say, well, that's not so bad. It just looks like a polynomial. Except there's one small detail that makes it not a polynomial. What's that small annoying detail? Yeah, the absolute value. So what do you do when you have absolute value? Well, what you can do is break it up. Because absolute value really is a piecewise function. Parts of it, when you have absolute value, says, look, I don't even need the absolute value. So in particular, if x is positive, I can drop those absolute values. Other parts, I need it. And so if x is negative, I'm required to have that absolute value. So if x is greater than or equal to 0, this becomes x squared plus 4x plus 3 over x squared minus 2x plus 1. In other words, I don't need them. Not useful. If I'm below 0, well, the absolute value does what? It flips the sign. So I can drop the absolute value, but if I do it, I need to change the sign. So that becomes x squared plus 4x plus 3 over x squared plus 2x plus 1. Now, this last part right here, if you stare at it, you might say, hey, wait a second. The top factors nicely. X plus 1, x plus 3. And the bottom factors nicely. X plus 1, x plus 1. So that you get a little bit of cancellation. So that really you have two things. You have x squared plus 4x plus 3 over x squared minus 2x plus 1. And that's if you're greater than or equal to 0. Or you have x plus 3 over x plus 1, and that's if you're less than or equal to 0. All right. And now that's the start of the problem. Okay, so what do we see? Well, we have two sides. And so we can handle them separately. Now, the nice thing is at 0, the function is fine. You're going to get 3 over 1. And so we can handle them separately. So notice it says all asymptotes. So there's two things to look for, horizontal and vertical. Well, let's do horizontal really quickly. So let's look at the limit as x goes to infinity of f of x. Now, since I'm going to positive infinity, I look at the part where I have the greater than or equal to 0. So this becomes the limit as x goes to infinity of x squared plus 4x plus 3 over x squared minus 2x plus 1. Now, right now, we can see it's a big number over a big number because you have the x squareds. But you have x squareds on both top and bottom. So it's the same thing that's driving the growth. It's the x squareds. So all right, so we're going to pump our brakes and slow it down. 1 over x squared. Multiply top and bottom. And if we do that, we get the limit. X goes to infinity of what? Well, 1 plus 4 over x plus 3 over x squared. That's upstairs 1 minus 2 over x plus 1 over x squared. And now we see that anything with a x or an x squared downstairs gets small. And so the limit is 1. Now, alternatively, what you can do is if you do see the case where it's a polynomial over polynomial, and you have that the highest degree is the same, so like here they're both second degree, then the answer is just look at the leading coefficients. The reason is you do what we just did. If you divide out by the growth of the highest degree, then what will happen is everything that's not a leading coefficient goes away. So for instance, we can do the same thing that we did before. So to negative infinity. So negative infinity of f of x, but now what do we do? Well, we can use this function here. Limit as x goes to negative infinity of x plus 3 over x plus 1. We say, oh look, highest power, first degree, they're both 1 coefficients, so it's 1. All right, so what do we conclude? Well, if we're making a list of asymptotes, we say that we have a horizontal asymptote at y equals 1 because we approach the value of 1. Okay. What about vertical? Well, there's a question. Where do you look? Now, if you're looking for a vertical asymptote, where you're looking for is you say, okay, well, first off, where's the function not defined? Because your function should basically be blowing up. When you have functions that look like polynomials over polynomials, if your denominator is not 0, your function is fine. There's nothing to do. So looking at this, we have to say, well, if we're worried about a potential asymptote, we need to say what happens when we have something that's 0. Now, if I look here, in the x greater than or equal to 0 case, and look downstairs, we see, okay, well, it's x squared minus 2x plus 1. Another way to write that is x minus 1 quantity squared. And we say, all right, so there's a potential asymptote at 1. And so we see it. So at x equals 1, we see that we have the limit. X goes to 1 of, and I'll write this, x squared plus 4x plus 3 over x minus 1 squared. Well, upstairs would be 1 plus 4 plus 3. That's 8 over 0. But we can be a little bit more specific. So first off, we shouldn't say 8 over 0 because that's not a thing. But it's going towards 8 over 0. So what's happening here? Well, we look at the denominator. I'm near 1. So x minus 1 is near 0. But x minus 1 squared is really near 0, positive. So what's happening is it's 8 over, and here's the key thing, this is a small positive number. And by that, I mean that when x is close to 1, I have a very small positive number, and I'm close to 8 upstairs. So it's a number over a small positive number, and therefore this is going to 1. So at x equals 1, I have a vertical asymptote of plus infinity both sides. In other words, it doesn't matter. So if I approach from the right side, it goes up. Approach from the left side, it goes up. And that's the only part I have to worry about if x is greater than or equal to 0. Now, when x is less than or equal to 0, it's even simpler to see because we already factored. You got that x plus 1. So what happens at negative 1? Well, at x equals negative 1, when we're looking at the limit, as x goes to negative 1, we have x plus 3 over x plus 1. Well, it's going to negative 1 plus 3 is 2 over 0. But now we have to be careful. Okay, well, what happens with here? Well, the 2 is near 2. So we're not worried about the top. It's the 0. And the question is, what kind of 0? So let's suppose for a second I look at x plus 1. So if I'm above negative 1, in other words, a larger value than negative 1, then x plus 1 will be positive. So now I'm defined by a small positive number, so the result is a big positive, and so it's going towards infinity. If I'm below negative 1, so negative 1.00001 as an example, x plus 1 is a small negative number. Okay, well, then if I divide by that small negative number, that gets a big negative number. And so I'm heading towards minus infinity. So now we have a different behavior. See, at x equals 1, we were going up on both sides. And at negative 1, well, we're sort of diverging. They're going in different directions. So we have a vertical asymptote of plus infinity to the right, and a vertical asymptote of minus infinity to the left. So pictorially, what's our function look like? Well, we know we have a horizontal asymptote at 1. So here's our y equals 1. We know we have a vertical asymptote here going on at x equals 1. So there's our vertical asymptote, x equals 1. And we also have a vertical asymptote here at x equals minus 1. And we happen to know, because we can plug in 0, we mentioned it before, it crosses at 3. So what's going on? Well, we know that from the left of negative 1, it's going to go down to minus infinity. So in fact, it's going to look something like this. It's going to come off the horizontal asymptote and go down. And then, from the right of negative 1, it's going to be, see, it's going to go up to infinity. So here, we're going up towards infinity. And similarly, when we come to 1, we're also going up towards infinity. So we sort of have this U shape on this part. And now, from x equals 1, we go up towards positive infinity from both sides, and then this somehow heads down towards 1. So this is the shape of our function, something roughly like that. There might be some more interesting wiggles here and there, but that's the basic shape. And so what do we have? We have one horizontal asymptote, and we have two vertical asymptotes, and that's the behavior of the vertical asymptotes. So again, at x equals minus 1, different behavior from the two sides. At x equals plus 1, same behavior from the two sides. Now that's interesting. Of course, it's math. It's all interesting. That's why we do it.